Hello everyone, welcome back to my channel. This is Nipa Patel from the Math Masters, and today we are going to do next few questions of chapter 1 Relations and Functions exercise 1.1. Please like the video and subscribe to get the notifications for new and upcoming videos. Let's start. Question 2. Show that the relation R in the set R of real numbers defined as R equals A comma B, where A is less than or equal to B square, is neither reflexive nor symmetric nor transitive. So what R we are given? R equals A comma B, where A is less than or equal to B square. Now let's start with reflexive. And since we are supposed to show that it is neither of these things, so we cannot actually prove it, we just need to show the counter examples. We just need to show the examples which prove that relation wrong. Okay, so we are going to start with reflexive. Now the definition of reflexive says what? That A comma A belongs to R for every A belongs to A. Let A is equal to 1 over 2. So if A equals 1 over 2, then we are saying 1 over 2 comma 1 over 2 belongs to R. Let's check, is that true or not? So A is less than or equal to B square. So in this case, A must be less than or equal to A square. Is that going to happen? Let's see, 1 over 2 less than or equal to 1 over 2 square. See, our A is 1 over 2. This A is also 1 over 2. So from this relation, this 1 over 2 must be less than or equal to 1 over 2 square. And that means we are saying 1 over 2 is less than or equal to 1 over 4. No, 1 over 2 is greater than 1 over 4. So this is not true. And since it is not true, so it is not reflexive. So it is not reflexive. We are going to check for symmetric now. Again, we are given that it is not going to be symmetric. So again, we are just going to show the counter example. Now the definition of symmetric is what? That if you have A comma B belongs to R, then you must have B comma A belongs to R. Now take A equals 1 and let's say B equals 2. So since A comma B belongs to R, that means we are saying that 1 comma 2 belongs to R. So let's say that this means 1 is less than or equal to 2 square. Is that correct? Yeah, it is correct. 1 is less than or equal to 4 because 1 is less than 4. So yeah, it is going to be true. So yeah, A comma B belongs to R. Now check for this part. B comma A belongs to R. So now B comma A means 2 comma 1 and 2 comma 1 means we are saying 2 is less than or equal to 1 square. Now 2 is less than or equal to 1. No, not true. This is not true. So we can say that it is not symmetric. So it is not symmetric. Why? Because we took A equals 1, B equals 2 and then check that 1 comma 2 belongs to R. Yeah, 1 comma 2 belong to R. And then we need to check for reverse of it, the converse of it, the other way around. So 2 comma 1. So 2 comma 1. So that means 2 must be less than or equal to 1 square. And it's not. It is bigger than that. So it is not true. So it is not symmetric. So now we are going to check for transitive. And again the same way, we are just going to present the counter example of it since we are already given that it is not going to be transitive either. So definition of transitive is what? That if you have A comma B in R and let's say if you have B comma C in R, then you must have A comma C in R. Okay, so this means what? That your A is less than or equal to B square. This means what? Your B is less than or equal to C square. And this means what? Your A is less than or equal to C square. Now we need to find a counter example that's going to make this wrong. That example must make this two true, but then this wrong. So let's take, okay, yeah, we can take b negative. So that's going to settle. So let a equals 2, b equals -3, and c equals -1. Okay, we are taking these values for a, b, and c. So if a is 2 and b is -3, so from this a less than or equal to b square, 2 is less than or equal to -3 square. Yeah, of course, makes sense because -3 square is 9, and yeah, 2 is less than 9. Now b is -3, c is -1. So b is less than or equal to c square. Let's check. -3. B is -3. So -3 is less than or equal to c square. C is -1. So -1 square. So -3 is less than or equal to 1. Yeah, of course, because -1 square is going to be +1 and -3 is going to be less than that. So yeah, this both make sense. So we have chosen the correct values for A, B, and C, or appropriate values for A, B, and C. Now we are going to check that whether this makes sense or not. Now your A must be less than or equal to C square. What was our A? A is 2. So 2 less than or equal to. Now C is what? -1. So -1 square. So -1 square is going to be 1. And is 2 smaller than or equal to 1? No, it's not. So not true. So it is not transitive. Question 3. Check whether the relation R defined in the set 1, 2, 3, 4, 5, 6 as R equals A, comma B, where B is equal to A plus 1 is reflexive, symmetric, or transitive. We need to check whether this given relation is reflexive, symmetric, or transitive. For that, what set you are given? Let that set A that you are given is 1, 2, 3, 4, 5, 6. So we are writing the same set. We are just letting that set is called A. And that relation, that definition that you are given, that B is equal to A plus 1. So let's now see that what elements are there in your R. So R is equal to, now if we take A equals 1, because our relation is what? From A to A. See, relation R defined in the set A. So that means our relation is from A to A. Now we need to take one number from A. So 1, and one of that number I'm taking as 1. So 1 plus 1, you are going to get 2 for that. If you take 2, then you are going to get 3 for that. If you are going to take 3, you are going to get 4 for that. Do you get that? Why I'm writing that? Because you are given this. You are given that B is equal to A plus 1. So if you take that first number as your A, because your A and A, they both belongs to this set only. Your relation is from this set to this set only. So if you take this number 1, then your B is going to be 1 plus 1 to 2. Now if you are going to take your A equals 2, then 2 plus 1, you are going to get 3. Now if you take your A equals 3, then 3 plus 1, then your B is going to be 4. So 3 comma 4. Same way, if you take 4, then 4 plus 1, so you'll have 5. If you take 5 as your A, then 5 plus 1, 6. And if you take 6 as your A, then 6 plus 1, 7. 7 is not in the set. So we need to stop here at 5 comma 6, because we cannot take A is equal to 6, because that belongs in A. But as soon as you are going to follow this 6 plus 1, that 7 does not belong in A. So we cannot use 6 is equal to A. We cannot use that part. So this many elements are there in our R set. Now we need to check for reflexive, symmetric, or transitive. Let's start with reflexive. Now definition of reflexive relation says what? That A comma A belongs to R for every A belongs to A. So you must have, see, in your A you have 1, 2, 3, 4, 5, 6. This 6 different numbers. So you must have 1 comma 1, you must have 2 comma 2, you must have 3 comma 3, 4 comma 4 in this R. You don't have any of those. So R is not reflexive, and the reason is that one because 1 comma 1 does not belong to R. You cannot see any of those, right? 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4, 6 comma 6. So it is not reflexive. Now we are going to check for symmetric. Now definition of symmetric says what? That if you have A comma B belongs to R, then you must have B comma A belongs to R. Now let's look at, okay, let's look at this 1 comma 2. So 1 comma 2 belongs to R. Yeah, we can see that in R. But then 2 comma 1, does 2 comma 1 belong to R? No. Why? Because your B is 1 bigger than A. So you will never have smaller number in the front. Why? You will never have, like, smaller number in as your second number in that coordinate pair. Why? Because your B is always going to be bigger than your A, right? Why? Because to get to B, you add 1 in A, and so A comma B, yeah, that is going to belong to R, of course. 1 comma 2 is in R. You can even take 2 comma 3 in R. Those are all in R, but you cannot see 3 comma 2 in R. You cannot see 4 comma 3 in R. You cannot see 5 comma 4 in R. Why? Because the definition, then it won't be true, because you are given B equals A plus 1. So you will never have B comma A belongs to R. So it is not symmetric either. So R is not symmetric. And why it is not symmetric? Just one of the example. Because 1 comma 2 belongs to R, but 2 comma 1 does not belong to R. Okay, now we are going to check for transitive. Now definition of transitive says what? That if you have A comma B belongs to R and you have B comma C belongs to R, that means you must have A comma C belongs to R. Okay. Now we need to see 1 comma 2. It is in R. 2 comma 3. It is in R. Okay. Let's look here. 1 comma 2 belongs to R. We can see that. See, 1 comma 2 is in R. So we are taking A equals 1, B equals 2, and we can say 2 comma 3. We can see that 2 comma 3 is also in R. So again, see, our B was 2, here same, B is 2, and we are taking C equals 3. That is also in R. But can you see 1 comma 3 in R? 1 comma 3. Okay, we cannot see that. Why? Because our second number is exactly 1 bigger than that first number, and 3 is not just 1 bigger than this one. It is 2 bigger. So it won't be in this relation, because from this definition we cannot see this pair 1 comma 3. So this does not belong to R, and since it does not belong to R, so R is not transitive. Why? Because we can see 1 comma 2 in R. We can see this 2 comma 3 in R. See, both have 2 in common. So we must have 1 comma 3 in this R. But we don't have that element in here. So because it's not there, we can say that R is not transitive. Question 4. Show that the relation R in real set R defined as R equals A comma B, where A is less than or equal to B, is reflexive and transitive but not symmetric. Okay, so we are already given that this relation is going to be reflexive and transitive but not symmetric. We are just supposed to show that. Okay, so what relation we are given? Let me just rewrite that. R equals A comma B, where A is less than or equal to B. We are going to first check for reflexive. So let's check for reflexive. Now the definition of reflexive says what? That if you have A comma A, or you must have A comma A belongs to R for every A belongs to A. Now let's check that a comma a. Now will a going to be less than or equal to a? Of course, right? Why? Because let x comma x belongs to R, and if that belongs to R means from this condition x is less than or equal to x. Yeah, that is true. X is less than or equal to x. X is equal to x, right? So that means a is less than or equal to a, and that means a comma a belongs to R, and that means R is reflexive. Okay, so we had to show that it is reflexive. We just did that. Now we need to show about the symmetric, that it is not symmetric. Let's do symmetric now. Now definition of symmetric says what? That if you have a comma b belongs to R, then you must have b comma a belongs to R. So now since we know that it is not going to be symmetric, we don't need to prove it, we just need to show the counter example. So let a is equal to 3 and b is equal to 4. So that means we are saying that 3 comma 4 belongs to R. Is that correct? That 3 is less than or equal to 4? Of course, 3 is less than 4. So yeah, that is true. And does that mean that 4 comma 3 is going to belong to R? Is 4, and this implies that 4 is less than or equal to 3, which is not true. This is not true. So 4 comma 3 does not belong to R. 3 comma 4 belongs to R, but 4 comma 3 does not belong to R. So R is not symmetric. We were supposed to show that, we just did. Now we need to show that it is transitive. See, we were given that it is reflexive and transitive but not symmetric. So we showed that it is reflexive. We showed that it is not symmetric. And now we need to show that it is transitive. So let's start checking for transitive. Now transitive definition says what? That if you have a comma b belongs to R and you have b comma c belongs to R, then you must have a comma c belongs to R. Okay, and since this is going to be true, we need to prove that. So let xy belongs to R and let yz belongs to R. Now if xy belongs to R means we are saying what? What was the condition? A less than or equal to b. So that means x is less than or equal to y, and this means y is less than or equal to z. Now x is less than or equal to y and y is less than or equal to z. Of course, that is going to imply that x is less than or equal to z. And since it is less than or equal to z, since x is less than or equal to z means a is less than or equal to c, and that means a comma c belongs to R, because it fulfills that condition that you are given. What condition? That a must be less than or equal to b, and c, a is less than or equal to c. That means a comma c belong to R, and since a comma c belongs to R, we can say so R is transitive, and we were supposed to show that, and we just did. Question 5. Check whether the relation R in real number R defined by R equals a comma b, where a is less than or equal to b cube, is reflexive, symmetric or transitive. So we need to check whether it's going to be reflexive, symmetric or transitive, and this relation you are given. So you are given R is equal to a comma b, where a is less than or equal to b cube. And we need to check for reflexive, symmetric and transitive. So let's start with reflexive. Now definition of reflexive relation is what? That a comma a belongs to R for every a belongs to a. Now if we take some number like 1, 2, 3, of course it's going to be correct, but what, it must be correct for all the values in a, right? it must be correct for all values in A. Here our A is R because that relation is defined in R. So if I want to write, I can write R over here. So that A must belong to that R. R is real number set. And it is not going to be true for all A. Why? Let's check. So if I take some fraction for A, 1 over 2, 1 over 3, 5 over 6, some fraction in between 0 to 1, if I take any fraction, let's take 1 over 2 for now, that is going to prove it wrong. Why? Because if A is 1 over 2, that means we say that 1 over 2 comma 1 over 2 belongs to R, and that means we are saying that 1 over 2 is less than or equal to 1 over 2 cube. But this is not true. This is not true. So A comma A does not belong to R, and so it is not reflexive. Why? Because 1 over 2 is greater than 1 over 8. You are doing cube of this. So it's going to be 1 over 8. So 1 over 2 is way bigger than 1 over 8. So it's not true. So that's why it is not reflexive. Now we are going to check for symmetric. Now definition of symmetric says what? That if you have A comma B belongs to R, then you must have B comma A also belong to R. Okay, so for that we can take, let's say, okay, let A is equal to 1 and B is equal to 2. So that means we are saying 1 comma 2 belongs to R. Is that correct? 1 less than or equal to 2 cube? Of course, yeah. So 1 comma 2 belongs to R. That is correct. But does that mean 2 comma 1 belongs to R? Because if 2 comma 1 belongs to R, that means we are saying 2 is less than or equal to 1 cube. Not true. Not true. So 2 comma 1 does not belong to R. So R is not, so it is not symmetric. So it is not symmetric. Now we need to check for transitive. Now definition of transitive says what? That if you have A comma B belongs to R, and if you have B comma C belongs to R, then you must have A comma C belongs to R. Okay, so for this we have to try like few numbers, and we might end up getting some counter example. And if we end up getting a counter example, that means that is not transitive. So for this, let's take A equals 9, B equals 4, and let's take C equals 2. Let's say this works or not. So if A is 9, B is 4 and C is 2, that means A comma B belongs to R. So we are saying 9 comma 4 belongs to R. Is that true? The condition is what? A must be less than or equal to B cube. So first number must be less than or equal to the cube of the second number. So 9 is less than or equal to 4 cube. 4 cube is what? 64. So of course 9 is smaller than 64. So yeah, this belongs to R. Now B comma C belongs to R. We took 4 and 2 for that. So 4 comma 2 belongs to R. So again, this first number, is it less than the cube of the second number? So cube of 2 is 8. So yeah, of course 4 is less than 8. So yeah, that also belongs to R. So this both element belongs to R, and that means from this transitive definition, we must have 9 comma 2 belongs to R. Why? Because see, 4 is in common in both of them. So if 9 comma 4 is in R and 4 comma 2 is in R, that means we must have 4 comma 2 in R. So it can be transitive. So 9 comma 2. If you check this, first number must be less than the cube of the second number. So this implies that 9 is less than or equal to cube of 2. Not true, because cube of 2 is going to be 8 and 9 is not less than or equal to 8. It is greater than 8. So not true. And since we found a counter example, so it is not transitive. Question 6. Show that the relation R in the set 1, 2, 3 given by R equals 1, 2, 2, 1 is symmetric. So this relation is symmetric but neither reflexive nor transitive. So we need to show that. Okay. So we are going to say, because we are not given the name for this set, so I am going to let A equals 1, 2, 3 and R we are already given, and we are given R is equal to 1, 2 and 2, 1, and we are going to start with reflexive. Now definition of reflexive is what? That you must have A belongs to R for every A belongs to A. So if you have, see 1, you can see in that set A, so you must have 1, 1 in here. We don't have that. 2, 2 in here. We don't have that. 3, 3 in here. We don't have that. So it is not reflexive. So R is not reflexive, and the reason is because 1, 1 does not belong to R. Now let's check for symmetric. Now definition of symmetric relation says what? That if you have A, B in R, then you must have B, A also in R. So that means, see 1, 2. You have this 1, 2 belongs to R. We can see that, see 1, 2. But that means from symmetric definition, you must have 2, 1 belongs to R. Oh yeah, we have that, see. We have 2, 1 belongs to R. So it is symmetric. And yeah, we were supposed to show that it is symmetric. So we got that it is symmetric, and we don't have any other element in that R that we can prove otherwise. So 1, 2 was in R, and we got 2, 1 also in R. So yes, R is symmetric, right? We were supposed to show that this relation is symmetric. We showed that, but neither reflexive nor transitive. So we showed that it is not reflexive. Now we need to just check for transitive. Now for transitive, the definition is what? That if you have A, B belongs to R and you have B, C belongs to R, then you must have A, C belongs to R. Now in this case, you got just these two elements. Let's check whether we can use those or not. Okay, yeah, looks like we can. So A, B belongs to R. Let's say 1, 2 belongs to R. So we are taking A equals 1, B equals 2, and we got 2, 1 in R. So again B is 2. So yeah, we are doing correct. So B is 2 and C is 1. Now, so from this definition, A, C. So our A was 1, B was 1. So we are saying that 1, 1 also belongs to R, which is not. So it does not belong to R. So it is not transitive. So R is not transitive. Why it is not transitive? Because 1, 1 does not belong to R. Question 7. Show that the relation R in the set A of all the books in a library of a college given by R equals x, y, where x and y have same number of pages is an equivalence relation. Now, what is an equivalence relation? When a relation is all three, all reflexive, symmetric and transitive, that means it is an equivalence relation. And since we need to show that this is equivalence relation, that means it is all these three. This relation, whatever you are given, that is reflexive, that is symmetric, and that is transitive. We just need to prove that. We just need to show that. Okay, and what relation you are given? You are given that that relation is x comma y, where x and y have same number of pages. So all the books in a library, the relation you are given is that when x and y have the same number of pages. This is the condition. Okay. Now let's start with reflexive. Now definition of a reflexive relation is what? That a comma a belongs to R for every a belongs to A. Now let x comma x belong to R. Okay, right now we are assuming that your A is equal to x. Now if A is equal to x, to be reflexive, x comma x must belong to R. And from that condition, that x and y have same number of pages, we can say that x and x have same number of pages. Yeah, it is true, because if we are talking about the same book, then yeah, that book will have same number of pages, of course. So x and x have same number of pages, which is correct. That means x comma x is going to belong to R. So x comma x is going to belong to R. That means a comma a is going to belong to R. And since a comma a belongs to R, means R is reflexive. So one down. We need to show all these three are true. We just showed that it is reflexive. Now we are going to start working on symmetric. Now symmetric definition is what? That if you have a comma b belongs to R, then you must have b comma a belongs to R. Now let x comma y belong to R. So if x comma y belong to R, that means x and y have same number of pages. Why? Because that's the condition. If you have xy in R, that means x and y have same number of pages. So can I write this same truth this way, that y and x have same number of pages? Is this correct? Of course, if x and y have same number of pages, then y and x have same number of pages. So that means y comma x belongs to R, and that means b comma a belongs to R, because our y was b and x was a. So yeah, of course b comma a belongs to R. And since we showed that b comma a belongs to R, we have shown that condition, that if a comma b belongs to R, then you must have b comma a belongs to R, which is true in this case. So R is symmetric. Now we need to just show the transitive. Now definition of transitive is what? That if you have a comma b belongs to R, and let's say you have b comma c belongs to R, then you must have a comma c belongs to R. Okay, so let x comma y belongs to R, and let y comma z belongs to R. Now we know that condition, that if xy belongs to R, that means x and y has same number of pages, and if y z belongs to R, then y and z must have same number of pages. Okay, so this means x and y have same number of pages, and this means y and z have same number of pages. Now if x and y has same number of pages and y and z has same number of pages, that implies that x and z have same number of pages. And if x and z has same number of pages, then we can say that x comma z belongs to R, and that means a comma c belongs to R, and that means R is transitive. Okay, so we were supposed to prove these three. Why? Because we were supposed to show that this relation, this relation R which you are given is equivalence relation. So we are going to be able to prove when and then that when we prove that it is reflexive. So yeah, it is reflexive. When it is symmetric, yes, it is symmetric. And when it is transitive, when the relation is all three, then and then it is equivalence relation. So we are going to write hence R is an equivalence relation. Question 8. Show that the relation R in the set A equals 1, 2, 3, 4, 5 given by R equals A comma B where mode of A minus B is even. And we need to prove that this is an equivalence relation. Then show that all the elements of 1, 3, 5 are related to each other and all the elements of 2, 4 set are related to each other. But no element of this set 1, 3, 5 is related to any of this 2, 4 element. Okay, so we got two different parts of this question. So first we are going to do up till here. The question up till here. What are we given? We are given A is equal to 1, 2, 3, 4 and 5 and you are given R is equal to A comma B where mode of A minus B is even. So we are given this relation. And we need to show that it is equivalence relation. What was equivalence relation? That when a relation is all three, reflexive, symmetric and transitive, then it is an equivalence relation. So we are just going to work through all those three and we are going to show that this relation is all those three, and then we are going to say that since it is all three, it is an equivalence relation. So first let's start with reflexive. Now definition of reflexive is what? That A comma A belongs to R for every A belongs to A. Now if we say let x comma x belongs to R. If x comma x belongs to R, that means mode of x minus x must be even. And is it even? You are going to get what? 0. So yeah, of course 0 is even. So yes, x comma x belongs to R means A comma A belongs to R. So R is reflexive. Okay, so we proved one of those. Now we are going to work through symmetric. Now definition of symmetric says what? That if you have A comma B belongs to R, then you must have B comma A belongs to R. Okay, so for this let x comma y belongs to R. Now if x comma y belongs to R, that means mode of x minus y is even, right? That's what we are given, right? Relation R A comma B where mode of A minus B is even. So if there is xy element in that set R, that means x minus y, mode of x minus y must be even. Okay, now if I change little bit this way, that I change the sequence of this. If I take negative sign out in the common, then y minus x. So mode of negative of y minus x, it's same thing as this. See, negative y and negative times negative x. So x minus y, this is same thing. So mode of negative of y minus x is even, of course, because I am writing the same thing. And since this is mode, it is actually what? Y minus x is even. And if y minus x is even, that means we are saying that y comma x belongs to R. And if we are saying that y comma x belongs to R, that means we are saying b comma a belongs to R. And b comma a belongs to R means R is symmetric. Now we are going to work through transitive. Now transitive definition says what? That if you have A comma B belongs to R, and if you have B comma C belongs to R, that means you must have A comma C belongs to R. Now let X comma Y belongs to R and let Y comma Z belongs to R. So this means we are saying that mode of X minus Y is even. And if it is even, I can write this way, that 2 times m, some constant m, since x minus y is even. Since mode of x minus y is even, I can say that it is 2 times m, where m can be any number. And since y comma z belongs to R, I can say that mode of y minus z must be equal to let some other constant. So 2 times n. And if I want to get rid of this mode sign, this absolute value sign, then I am just going to do x minus y equals plus minus 2m and y minus z is equal to plus minus 2n. Our aim is to show a comma c. In this case, in xyz case, we want to show x and z, we want to get rid of y. We want to eliminate y. So how can we eliminate y from this and this equation? We just need to add them. We just need to add them. As soon as you add them, you are going to get what? X minus y plus y minus z equals plus minus 2m plus minus 2n. And then y and y is going to cancel out. You will get x minus z equals, now I can take plus minus and 2 in the common, and then in the parenthesis you will have m plus n. So from the result we can literally see x minus z is 2 times something, right? X minus z is 2 times something. So yeah, it is even, right? We were supposed to prove that x comma z also belongs to R. So this implies that x minus z is even, and that means x comma z belongs to R, and that means a comma c belongs to R. So R is transitive. And since, or hence, R is an equivalence relation. Hence R is an equivalence relation. Now we are going to do that second part of the question. So second part of the question was what? That you were given that show that all the elements of 1, 3, 5 are related to each other. So we are supposed to show that elements of 1, 1, 3, 5 are related to each other. So still our R is the same. So let me just rewrite that R is A comma B, where mode of A minus B is even. Okay. Now this implies that set 1, 3, 5, that's what we are supposed to work on, is related to each other, is related to each other. And why it is related to each other? Because difference of odd, see 1, 3, 5 all are odd numbers. So difference of 3 and 1, or difference of 5 and 3, or difference of 5 and 1, or even other way around, because we are given absolute sign. So other way around, they are all going to be even. So they are related to each other because of odd natural numbers or odd numbers is even, right? Because I never wrote difference. Okay, so 1, 3, 5 is related to each other because the difference of odd numbers is even. So that's why 1 comma 3 comma 5 is going to relate to each other. Now we need to show that this 2 comma 4 elements are related to each other. So 2 comma 4, they both are even. So again the difference of 2 comma 4 are going to be even, right? So 2 comma 4 are related to each other. Here also are, right? Are related to each other because the difference of even numbers is even. Okay, now third part of that second question is what? But no element of 135 is related to 24. So difference of any element from this to any element of this is not going to be even. Like, find the difference of 5 and 2, or even 3 and 2, or 1 and 4, or 3 and 4, or 5 and 4. It is not going to be even. So 1, 3, 5 are not related to 2 comma 4 because difference of odd, I don't need to write natural, difference of odd number and even number is odd. So here we were supposed to show that in the first part that it is an equivalence relation, which we did because we proved that it is all three. It is reflexive, it is symmetric, it is transitive, and then we said that hence R is an equivalence relation. And in that second part we were supposed to prove that 135, it is related to itself. So yeah, because difference of any two elements in this, it's going to be even. So yeah, it is going to be related to itself. 2, 4, both are even. So again, difference of any two numbers in this, it's going to be even. So that is also going to be related to itself, 2 comma 4. But from 135 to 2, 4, these are all odd numbers, these are all even numbers. So difference of odd and even, it's never going to be even, it's always going to be odd. So it's not related from 135 to 2, 4.
Okay, so that's it for today. We'll do remaining questions in the next video. Please like the video and subscribe, and see you all soon in the next video. Bye.